Hello and welcome to the second video in this topic on data representation. In this video, we're going to look at the conversion from a denary number into a binary number into a hexadecimal number and all the way back. So for the first question, we're going to look at denary to binary. And the question is, using 8 bits, convert 38 in base 10 to binary, which is base 2. First thing I like to do is answer what the question has asked me. So using 8 bits. So what I do is I write out my 8 bits going up in the power of 2. Once I've done that, I take 38 and I try to see if 38 will go into 128. It won't. So I move to 64. It won't go into that. I move to 32. I can get one lot of 32 out of 38. And that leaves me with 6 left over. And I try to take 16 out of 6. I can't do that. I try to take 8 out of 6. I can't do that. I try to take 4 out of 6. I can do that. It leaves me with 2 left over. I try and take 2 from 2. Yes, I can. And that leaves me with nothing left over. So 1 is 0. And that leaves me with my binary number as 001. 00110. Then what I do is I always check my answers, and it's a great idea to do this if you have time in your exam, is to write down the numbers and add them up to see if it makes your base 10 number that you started off with. So let's do another question then. Hopefully you're getting the hang of this now. Using 8 bits, convert 173 in base 10 to binary. First thing I do is I write out my 8-bit values. I take 173 and say, can I take 128 from that? Yes, I can. That leaves me with 45 left over. I say, can you take 64 out of 45? No, I can't. Can you take 32 out of 45? Yes, I can. So I put a 1 there. And that leaves me with 13 left over. Can I take 16 out of 13? No, I can't. Can I take 8 out of 13? Yes, I can. That leaves me with 5 left over. Then I try and take 4 out of 5. I can do that. That leaves me with 1 left over. Can I take 2 from 1? No, I can't. Can I take 1 from 1? Yes, I can. And again, I quickly write the numbers down and add them up to make sure I've not made any mistakes. And that looks good to me. Okay, this time let's go from binary to denary. And here is my binary number, 0101101. First thing I do is I put my binary numbers at the top. And then all I do is wherever I've put a 1, I will just add the values. So I take 64, 16, 8, 4 and 1. And then all I have to do is add those together. So adding those is 23 plus 6, 7, 9, 93. That is my final denary number. Now we're going to look at a base 2 binary number into hexadecimal, which is base 16. And this method is a very, very simple method. It's pretty foolproof, really. So I'm going to use the 8-bit binary number 011011110. And the first thing you do, step 1, is to break this 8-bit number down into nibbles. So I'll break it into 2 nibbles because there's 4 bits in a nibble. Once I've done that, I will write my values above my binary digits. So I write 1248 and 1248 because they are separate nibbles. And then I just add up the values, and that gives me 6 on the left-hand side and E on the right-hand side. And why does it give me E? Because remember, we go from 1 to 9 and then A to F. And that is because we've only got 4 bits, which gives us a maximum value of 15. So all I'll do is fill in what the binary values are for my hexadecimal scale. And if you do this in your exam, you'll save yourself a lot of time. Although be careful, because some people, if you get 1 bit wrong, then it can mess everything up. Okay, we'll do one more of these binary to hexadecimal conversions, and then we will move on. So same process applies. I've got 0110101. I split them into nibbles, I apply the values on the top, and then just add the values, and I've got 6 and 12, 13, that's D. Now it's suddenly become much easier with the table on the right hand side. But what about going backwards from hexadecimal into binary? So here's the question, 9E. The same process applies. You break them in half and you convert the number 9 into binary, and E, which equals 14, you turn that into binary using 4 bits, and then all you do is concatenate or add together the two nibbles to make a byte. So the final answer here is 100111110, and that's our binary number. So far so good. So you can have a go at this one. You can pause the video if you want to. I'm just going to go ahead and do it. So I split it in half, apply my binary values. I've got F, which is 15 and 2, which is fairly simple. So that gives me 1, 1, 1, 1, 0, 0, 1, 0. So it's quite a quick process now when we know what we're doing. So that's quite simple. What about going from Deanery all the way to hexadecimal, or all the way from hexadecimal back to Deanery? So you can do this now. You just apply what you already know. You move your Deanery number, 156, into binary. So I take 128 from there. That leaves me with just 28 left. So I take 0 64s, 0 32s. I can take 1 16, and that leaves me with 12. I can take 1 8 from there, 1 4 from there, and 0 for 2 and 0 for 1. So if I add all those up, that will add to 156. And to convert my binary number into hexadecimal, all I have to do is split them into nibbles. So I split the whole byte, all 8 bits, into nibbles, apply my values on top, and then add up the numbers. So that's 8 and 1 is 9, 8 and 4 is 12, and I know 12 is C, so that means the hexadecimal value for the Deanery number 156 is 9C. So let's reverse that process. Let's go from hexadecimal number 98 base 16. So to reverse that, all I'm going to do is split it in half. I convert 8 into a 4-bit binary number, 1000, and I convert 9, 1001. I put them two together to make my binary number, and then I convert that binary number into Deanery. So I take the values 128, 16, and 8, and I add them all together, and that equals 152 in base 10. So hopefully you can see the process now where we can apply Deanery numbers to binary numbers, and then binary numbers into hexadecimal, and then all the way back. So let's try one final example. Let's take A, B. And A has the value of 10 and B has the value of 11, and I need the 4-bit binary number equivalent of 10 and 11. So for 11 it's 1011, and for A it's 1010. I put them two together to produce my binary number in base 2, and then I convert that binary number into Deanery by putting all my binary values at the top and simply add the numbers 128, 32, 8, 2 and 1. So that produces 21 plus 50, 70, 171. And that's my base 10 equivalent of the hexadecimal AB. So that was a really quick stop at converting Deanery to binary to hexadecimal and all the way back. Hopefully you've learned something, and if you need to go back over the video, that's not a problem. Just rewind it and have another go. Other than that, I'll see you in the next video where we'll look at negative binary numbers.